the code that you've been looking at there is so simple, you would never do it on a GPU. So let's look at a code that's slightly more realistic, but still simple. And why do I say it's still simple? It's simple enough that you can just look at the code. It's about 200 lines. So you can look at the code, you can understand what it's doing. When somebody gives you a full application, and it's thousands, tens of thousands, hundreds of thousands of lines, you don't just look at it and know how it works. It's a major job to understand the code. So that's not the code to start with. And in the practical that goes with this, you'll actually, oh, am I not on? I'm on now. Right, thank you. In the practical that follows, practical 2, you actually get to look at this code. So you don't need to worry too much about taking notes on what I'm doing. What is the code? It's called the Himeno Benchmark, not that that matters. It's a stencil code. It's doing a finite difference on a 3D array. This finite difference is, it uses nearest neighbors and next to nearest neighbors. So altogether there are 18 points and the central point used to make up that stencil. It's quite a memory-intensive, memory bandwidth code. It doesn't do a very complicated calculation based on this data, but it's still a good example to use for this sort of thing. There is a parallel version. I'll talk a little bit about the parallel version this afternoon, but we're just looking at this, the single MPI rank, if you like, the single CPU, the single GPU version. Why a simple code? Well, because we've already said, if you want to port a code, you need to understand stuff about the application. The main things that you need to understand are, how does data move? What arrays are used? Which routines use these arrays? How do they process these arrays? Because you want to port so that the arrays move between CPU and GPU as little as possible. Ideally, never, that they just live on the GPU forever for the whole application. That's the biggest optimization you'll ever make in your GPU code. And the other thing is, well, how do I get started? You need to know something about, OpenACC is really about loop-based codes. It's not about very task-based codes. It's about accelerating loop-based codes, which you see in science, engineering, this sort of thing. Which loop nests dominate the runtime? Are they suitable for the GPU? How many trips, how many iterations are there? If they're very small loop nests, they're not going to work very well. GPUs need a lot of threads going to be efficient. So for a big application, you need tools to do that because it's such a big problem. But if we start with a simple code, you can do it by eye. And that's why we're doing this example. So the first step in accelerating is understand something about the application. Profile it, look at the code, speak to the developers. You need to know how the application works and what are the important arrays and how are they used and this sort of thing. Then you start by starting. You make your first OpenACC kernels. Then you want to start putting in data regions because you want to start minimizing data transfer. You start doing that down in the low levels of the call tree. But eventually you're going to move up the call tree so that more and more of your application is within bigger and bigger data regions so that your arrays never move. Once you've done all of that, once the data isn't moving more than it has to, then think about performance tuning, kernels. But don't worry about, as long as they're not stupidly slow because they're doing something ridiculous, just get your kernels going, get the data movement sorted out, and then think about optimizing kernel performance. And remember Amdahl's law. If the GPU speeds up your kernels even a bit, you may end up with, actually, compute is not the slow part of your application anymore. It's MPI transfers. It's I/O. So maybe the optimizations that you're making is not kernel performance. The real optimization is trying to optimize the way you use MPI or trying to optimize how you do your I/O in your program. So, work on the bits that are slow. This simple code is very simple. It has two routines in it. The one initializes the data, called at the start of the program, and the other does an iterative stencil update on the array. So it takes the array, it processes it, it writes it back on the original array, and then it does that a certain number of iterations. This routine is called twice. Not that that matters. The first time is just for calibration, just to get an idea of speed, because it's a benchmark code. The second time it says, well, OK, I'm going to run this for 30 seconds. So I'm running it for long enough I get a good performance measurement. So the next slide looks at an edited version of the code. I'm going to mainly talk about the Fortran version. The C version is there in your tar file as well, so you can see how you do it in C. So here's the main program. It calls the initialization. It times 3 iterations. It uses that time that it measures to estimate how many iterations it should do for the full test. And then it does that number of iterations, and from that, it does a little calculation to give a megaflops performance. And it also prints out, this is the residual error. So it's got 2 important features here. It's got a timer, and it's got an error. If your code is accelerated correctly, the error should be the same, because the error is how the algorithm is working. If that value changes, it's like a checksum, you know that you've done something wrong in your accelerator port. So anytime you do a port, make sure you've got some sort of correctness check, and it's also nice to have a timer. Now here, I'm actually fixing the number of iterations. Clearly, this error will vary as you change the number of iterations, because it's an iterative algorithm. So I'm fixing the number of iterations here. So every time I do CPU or GPU, it always does the same number of iterations. If you look inside this Jacobi routine, what does it do? First of all, it takes the data array P, and it does an update into a temporary array. And then it copies the temporary array back into P, and then it does another iteration. And this residual, this error, apparently GOSA is Japanese for calculational error, I'm told. And since it's a Japanese code, that's what. So this is calculated in this stencil here, which I've not shown. And the halo is fixed. So values 1 and Imax or Jmax or Kmax don't change. The halo is fixed for this calculation. The actual stencil looks like this. Well, it's kind of a bit complicated. But basically, triple loop nest, not looking at the halo. Here's the stencil. So you've got nearest neighbors, you've got next to nearest neighbors, forward and backward. Then you've got nearest neighbors backward, and the central value are all combined together with some appropriate weight factors that are there. The error is added up as you go, and this is the updated value of the array. So GOSA is what you would call a reduction variable, because it's something where you get one value out from the entire loop nest. And this kernel dominates the runtime. It's something like 98% of the runtime. So all the other loop nests that are in the code, the other 3 loop nests, one that I've just shown before where work 2 is copied back into P, and the 2 loop nests in the initialization have no bearing on performance. So what do we do? Well, obvious thing to do is start with the slowest routine. The slowest routine is this stencil, so what do? Well, we say it's a parallel loop. I've renamed this here. The reason it's renamed is to make it compatible with the OpenMP version, but the error is set to be 0 outside, so no race conditions. And then I say it's a reduction variable, and I'm doing a sum to get the final answer. So that's the little clause that you use. I've said the scalars are private. I didn't need to. And then I've said these arrays are read-only. This array is write-only, so I've said them copy in and copy out. And that's the acceleration. So that's, just like I said, that's all you needed to do. And I didn't actually need to put in these array movements. It would have done it automatically. But I've just put them in to show you. So then you compile it. Compiler feedback is really important. Did it compile the directives or not? How will the compiler move the arrays? Only use data clauses if the compiler is being overcautious. Otherwise, just let the compiler do it. Or if you want it to be a temporary array. And the first optimization is always removing the unnecessary data movements. And then how is it going to schedule it across the GPU? So you generate this information with PGI or with Cray by an appropriate flag, and that gives you this information. It's free. Please look at it. It doesn't affect performance. If you look at the Cray stuff, it looks something like this. Here's the loop nest. Suddenly, what's appeared is these capital Gs. What do the capital G up here mean? What this means is that this region was indeed put on the GPU. Here's the source line numbers. Here's the original source. The outer loop, the iteration loop, just has a number down the side. What does that mean? It means this loop is going to be done sequentially, serially. You don't parallelize the iteration loop, obviously. And then inside this stencil, the K loop has a little G down the side. That means it's been divided over the threads of the GPU. The I loop has some Gs down the side. That means its iterations have also been divided amongst the threads of the GPU. The K loop just has a number. What does that mean? The number means that this, just like the outer loop, this loop has remained sequential. So, data movements. Underneath this source listing, you'll find a set of measurements, a set of messages. Each of them has a little thing at the beginning that you can use the explain command for. It gives you the line number. And it says at the start, if it is not already present, allocate memory and copy the whole array P to the accelerator. And at line 191, the end, you should free that memory, but not copy it back. That's the copy-in directive it's telling you. And the identical messages for the other arrays. But when you look at the message here about work 2, it's saying, allocate memory and copy the whole array work 2 to the accelerator. Work 2 was scratch space, but the compiler wasn't sure about the edges. So it said, oh, to be sure, I'm going to move that array. So it was being overcautious. So that's why you would step in and say, actually, copy out is fine, because you don't need it. The initial values don't matter. The scheduling. It's said here that the K loop is partitioned across the thread blocks. That means, if you think about CUDA, each thread block will be doing a different value of K. If you don't think about CUDA, don't worry about it. The middle loop wasn't partitioned. It was redundantly executed. The inner loop was divided across the threads within a thread block. And by default, it's using 128 threads. That's like the thread IDX variable if you were using CUDA. If you're not using CUDA, you ignore that. So each thread on the GPU is going to do a particular value of I and a particular value of K. And for its particular value of I and K, redundantly means it's going to do a full J loop for its value of I and K. So if you were writing a CUDA kernel, within that CUDA kernel, there would be a J loop to process all the J values, and I and K would be fixed by thread IDX and block IDX. If you don't do CUDA, don't worry about it. But the important part here is that there's a division over thread blocks, and there is a division over threads within a block. If you don't see both of those, you're not using the GPU efficiently. We have a checksum to make sure the answer is correct. If there isn't one in your code, put one in. If at all possible, make that checksum double precision, because it's much easier to spot errors. When we do that, and we do the first kernel, the code goes, well, what does happen? The performance, well, is the code faster? No. It's got worse with Kepler, I think. The performance has actually gone down. Why has it gone down? The code is actually faster. The reason it's gone down is because it's only spending 2% of the time in compute. The rest it's spending shifting data to that kernel and back. Every iteration it does that. And you're doing, I don't know, 100,000 iterations. Far too much data movement. So if you're only spending 2% of the time on compute and you were spending 98% on the CPU, you can get a 49-fold speed up by getting rid of those data movements. You will never match that with a kernel optimization. So always do kernel optimizations after you've sorted out data movement. If you want, you can use the Cray tool to break down and actually profile the code. If you've used a profiling tool on the CPU, Cray has a profiling tool that works with both CPU and GPU called CrayPat. And you can use that to look at the, what's being spent. So I haven't really talked about asynchronicity, but if you switch off the asynchronicity, I mean, the exercise isn't about doing CrayPat. You'll see that a bit in Practical 3. But when you do that, you see all its time here is being spent in data movement, ACC copy at the start, ACC copy at the end, and the kernel is only taking 2% of the time. So what we need to do is cut down on data movement. So we need to put a data region in, and we need that data region to stop having to move the data backwards and forwards all the time. Now the problem is that, really, where's this data region going to go? Well, it's going to have to go outside the iteration loop. We don't want to move all of the arrays every iteration. So then so the data region should go outside the iteration loop, so we only move at the start and end. But there's another loop nest in that iteration loop that took no time in the profile, which just copied temporary array work 2 back into the data array P, ready for the next iteration. So we're going to have to port that to the GPU, not because it takes any time, but because if we leave it on the CPU, we've got to keep moving data backwards and forwards. So this is what I mean by sometimes you have to port extra code. This is a big win for something like OpenACC. Porting a loop nest that takes no time is one directive, because you don't even care about scheduling, because it takes no time. But otherwise, you'd have to write a whole CUDA kernel to do that. So OpenACC is a big win when you're trying to get these data movements. So this is what I do. I put a data region at the start of this Jacobi routine, outside the iteration loop, and it ends here. And there is where I say how the arrays are going to move. And work 2 is now just a temporary array, so I call it create. And then I have to say parallel loop around this extra loop nest. When I do that, what happens? Well, now things start to move. Suddenly the performance has gone from being like this and dropping down to here. The performance is now up at, something respectable. And we're way ahead of the CPU now. I mean, that was one core, but here you're not going to get this performance from the CPU. You can see that already. And we haven't done any tuning. We haven't worried about threads per block or anything like that. All we've said is parallel loop and a data region. Now 51% of the GPU time is compute. Data transfers are only happening once per call to this Jacobi routine. And the GOSA values, the error values, if we check them, are still correct. That's just what the profile looks like. Can we go further? Why don't we initialize those data arrays on the GPU, and then we never need to move them at all? So we want to now take a data region even further. So you can nest data regions. So I'm going to leave the data region that's in the Jacobi kernel, but it's going to be subject to another data region further up the call tree in the main program. So in the main program, I'm going to put a data region in here that's going to span the initialization call and the performance call to Jacobi. And here, the data is only going to move at the boundaries of this. So now we're really just timing GPU compute, not PCI bandwidth. Of course, what happens now is that because we're going to move the arrays here, we have to go into Jacobi and say, instead of the copy and copy in, we're now going to say, these are present. We're not going to say present or copy, because we know the only calls to Jacobi are inside this data region, so they're always going to be present. If this fails at runtime, we've broken our code somehow, and we want to know about that. Well, could we go further? The best solution is to port the entire application. We're still copying data in and out. So could we move the initialization routine into the data region as well? Why not? So we make the data region in the main program bigger, so it goes outside now the call to this initialization. Now, because we initialize the arrays on the GPU, we just label them all as being scratch space, create, no data movement at all. And that's what we do. So now the initialization goes inside. What that means is that go into the initialization routine. There's a couple of loop nests that set the initial data. We must make those kernels as well. And we must say that these arrays are already present. But it's so easy to put parallel loop directives in for these that it's almost no work. Again, you don't have to write a kernel to do this. You can do it with OpenACC. When you do that, the performance gets even better because you're not copying any data at all. And so now the performance is massively, it's improved a lot. We're now spending 98% of the GPU time on compute. Well, that's good. We were spending 98% before, kind of, on that big compute kernel. It kind of makes sense that the profile is balanced in the same way, only much quicker when you go to the GPU. If a routine that was very quick on the GPU, on the CPU, is one of the slowest on the GPU, that's often a time to go in and say, has it scheduled it correctly? It's maybe done something naively, sillily wrong. So we're now getting an 18 times speed up. In fact, that number's out of date. Because I had to redo all of these numbers for Kepler. The point is we're going so much faster than the CPU, but that was to one core. What happens if we run the OpenMP? Well, what did I say? Sorry. Before we worry about what we could do further, we need to check, is it all running correctly? We look at the list files, we look at these schedules, always just check these. Just run through them, just look at them. Do you see 2 little g's? If you don't, you're not seeing good GPU usage. I'll talk a bit more about what you do if you don't see that this afternoon. Don't worry about the performance, but just make sure it's not done anything really silly. Lunchtime beckons. I was going to talk about similarities between OpenMP and OpenACC. Maybe, shall I leave that until after lunch? Or do you want to hear about it now? Silence. Do it now. Right. If you've done OpenMP, listen. If not, don't worry. If you had the code that you've got actually has OpenMP in it. And so if you said, well, how would I do this with OpenMP? How would I start to do it? So you do it in a very similar way. You would say parallel loop here, and then you're adding up the residual. That's how you would do it with OpenMP. And that's very like what you're doing with OpenACC before you think about data regions up here. So there's a big similarity between the two. So if you have a code that's OpenMP, it can often be a good place to start for doing an OpenACC port because you can copy things. But the difference comes in that with OpenMP, creating a parallel region is expensive, and you try to do it as little as possible. So in the same way that with OpenACC, we worried about taking data movements outside the iteration loop, with OpenMP, you try and take the parallel region creation outside the iteration loop, and then you kind of go through, you have critical region, master region, a critical region, where you try to make sure that each thread, when it does the residual calculation, that they all add up correctly and you don't get race conditions. So at this point, an efficient OpenMP code starts to look like this. So should we do the same and take the parallel directive outside of here so we're not creating GPU parallel thread teams too much? No, because you'll hit race conditions. And GPU threads are really lightweight. They're really easy to create. So don't worry about it and don't try to do it. So you stick with this sort of picture for OpenACC, whereas in OpenMP, you might go more towards that. Now, as I say, if you don't do OpenMP programming, you don't need to worry about that. And this says a little bit about what I was saying there. If we do run the OpenMP version, so we can use all the CPUs, all the cores of the CPU, what happens? Well, it does improve performance from there to there or there to there for C, but it doesn't improve it by anything like enough to catch up with the GPU. So with no kernel tuning in OpenACC, just using parallel loop and data regions, we are going about 5 to 6 times faster than a full CPU, which for a memory bandwidth bound code is kind of what we'd expect just from the memory bandwidth ratios. What could we do extra? Well, I'll talk a little bit more about that this afternoon, about how you could do some performance tuning. But the biggest performance tuning was getting rid of the data movements. So 5 to 6 times full speed up with 7 directives in 200 lines. It's not bad. Of course, you say that's a very simple code. Real codes don't look like that. You'll never get that in practice. I'm kind of going to, we'll do a more complicated example this afternoon and kind of see what you can get there. But as simple codes go, you know, if you just want to explore what's happening, a code like this, it's always a good feeling to do not too much work and actually find the benefit. And you don't always get that because somebody always says, oh yes, well that was very naive, of course that wouldn't work. But here, a quite naive approach really does give you the performance boost. So I think we'll break for lunch, but there is a practical that goes with this afternoon where I've got 4 versions of the code, CPU, 1 kernel, data region outside the iteration loop, and then data region outside everything. So you've got the 4 versions of the code, and you can go through it and just, you know, if you want, just look at it, see the results of running it. But really, you should go in and have a look at it and start to see what's going on. Maybe even try generating some profiles to see some of these numbers yourself. But we'll do that this afternoon. So are there any questions? Still a good example to use for this sort of thing. There is a parallel version. I'll talk a little bit about the parallel version this afternoon, but we're just looking at this, the single MPI rank, if you like, the single CPU, the single GPU version. Why a simple code? Well, because we've already said, if you want to port a code, you need to understand stuff about the application. The main things that you need to understand are, how does data move? What arrays are used? Which routines use these arrays? How do they process these arrays? Because you want to port so that the arrays move. In the practical that follows, practical 2, you actually get to look at this code. So you don't need to worry too much about taking notes on what I'm doing. What is the code? It's called the Himeno Benchmark, not that that matters. It's a stencil code. It's doing a finite difference on a 3D array. This finite difference is, it uses nearest neighbors and next to nearest neighbors. So altogether there are 18 points and the central point used to make up that stencil. It's quite a memory-intensive, memory bandwidth code. It doesn't do a very complicated calculation based on this data, but it's between CPU and GPU as little as possible. Ideally, never, that they just live on the GPU forever for the whole application. That's the biggest optimization you'll ever make in your GPU code. And the other thing is, well, how do I get started? You know, you need to know something about, OpenACC is really about loop-based codes. It's not about very task-based codes. It's about accelerating loop-based codes, which you see in science, engineering, this sort of thing. Which loop nests dominate the runtime? Are they suitable for the GPU? You know, how many trips, how many iterations are there? If they're very small loop nests, they're not going to work very well. GPUs need a lot of threads going to be efficient. So for a big application, you need tools to do that because it's such a big problem. But if we start with a simple code, you can do it by eye. And that's why we're doing this example. So the first step in accelerating is understand something about the application. Profile it, look at the code, speak to the developers. You need to know how the application works and what are the important arrays and how are they used and this sort of thing. Then you start by starting. You make your first OpenACC kernels. Then you want to start putting in data regions because you want to start minimizing data transfer. You start doing that down in the low levels of the call tree. The code that you've been looking at there is so simple, you would never do it on a GPU. So let's look at a code that's slightly more realistic, but still simple. And why do I say it's still simple? It's simple enough that you can just look at the code. It's about 200 lines. So you can look at the code, you can understand what it's doing. When somebody gives you a full application, and it's thousands, tens of thousands, hundreds of thousands of lines, you don't just look at it and know how it works. It's a major job to understand the code. So that's not the code to start with. And in the practical that goes with this, you'll actually, oh, am I not on? I'm on now. Right, thank you.